Hello. So in this lecture, we will see about truth table for compound propositions, some laws required to solve some compound propositions or simplify them, and also we'll see about PCNF and PDNF. Let's say about truth table. So this is not new for you. You have already studied before, maybe in your schooling or in your +1, +2. So what is this truth table? You have to know given a compound proposition like this, which involves multiple propositions P, Q, P or Q or R, like this. If you are given a compound proposition, you have to construct its truth table. So how do you do this? So this is the lengthy expression given to us. So P, you write P, Q different. I think this you are aware of. How are we writing these different combinations? So when you have two variables P and Q, the truth table combination will be true, TT, TF, FT and FF. What if you have three variables P, Q, R? Then in that case, it is your TTT, then TTF, then TFT, FTT. Okay. Then you will have another case here where you write FFT, FTF, and you have FFF for all the case. Then the other case is TFF. Okay. So like this you have different combinations of three variables PQR. So when you have two variables you have 4, when you have three variables you have 8 such combinations. Then find out minus Q, then find out the first term P or minus Q, then find out P and Q value, and then find out the implication value. How am I writing these results here? It is based on the truth tables of individual. See, you know the truth table of disjunction, truth table of conjunction, truth table of implication. By using those concepts, I am trying to write this truth table. Okay, this is used for us to solve the problem. Why we are learning this construction of truth table? Because there are some concepts like logically equivalent and PCNF, DCNF. We need to always solve them using the truth table concept. So what are the different terms in compound proposition? See, when you have a compound proposition, if the final result of that is always true, then that kind of a compound proposition is called as tautology. It means here, if you have the final results all as true, then such kind of statements are called as tautology. And if there is always false in the final output, it is called contradiction. It means in this lengthy expression, if you have some expression like this, minus P implies minus Q or R, something like this. If I give any input here, it is always giving false as the output. Then that kind of a statement is called as contradiction. Then we have a special one here. Any statement which is not a tautology nor a contradiction is called as contingency. Okay. If it is not tautology and not contradiction, it is called as contingency. And if a compound proposition or if two compound propositions are always yielding same result in the truth table, then that kind of compound propositions are called as logically equivalent statements. Okay, compound propositions that have same truth values in all possible cases are called as logically equivalent statements. So we represent it like this: P with three symbols here, 3 equal to symbol. This is called logically equivalent. Okay, so sometimes they will ask questions like this: show that minus P or Q and minus P and minus Q are logically equivalent. So you have to construct truth table for this, and you have to construct truth table for this. See the final result. Are they same? If they are same, we say then that P and Q are logically equivalent. Okay. The other kind of question what we have here is P and Q implies P or Q. Show that it is a tautology. So construct the truth table. See the final column, the final result column. If every output is true, then we say we can prove that this given proposition is a tautology. So next one is precedence of logical operators. When you have different operators, we have studied 5 different operators: negation, conjunction, disjunction, and implication by implication. Among them, there is some priority. Like in programming also you might have studied, there is something operator precedence. Which operator will execute first when you have a very lengthy mathematical equation. In the same way, when you have these 5 logical operators, this is the ranking. First you have to apply negation, then you have to apply conjunction, then you have to go for disjunction, and implication and by implication. Okay, very important. Logical equivalence in set theory also we have studied about these kind of laws. Same laws exist here as well. See, if you take example of domination laws, P or true. See, with OR operator, we know that only if both are false, the result is false. Otherwise, it's always true. So here, P or true means always true. P and false means always false. Okay, like this we have idempotent law, double negation law, minus of minus P is P. They are logically equivalent. Commutative law is very common. P or Q is equal to Q or P. P and Q is equal to Q and P. Then we have some more laws here. Associative law. P or Q or R is equal to P or Q and Q or R. So any two combination A or B or C, these two is same as A or B or C. Okay, associative law. Distributive law, P or Q and R means P or Q and P or R, like this. Same for the reverse case. The very important is De Morgan's laws. Negation of P or Q. Apply negation to P, it becomes negation P. Apply negation to R, it becomes AND. Apply negation to Q, it becomes minus P. Okay, De Morgan's law is simple. Then we have absorption and negation laws. So we'll try to see these things. We use this in problem solving. Logical equivalence involving conditional statements. These are few with a lot of experience and research. They have listed down lot of logical equivalence. These are used for us to solve the problems quickly. So P implies Q can be written as negation P or Q. See the first law, negation P or Q. Okay, like this we have so many. See, P or Q can be written as negation P implies Q. P or Q can be written as negation P implies Q. That way we have some logical inferences here. These are very useful in solving the problems. So please note them down and practice them, remember them, which are very useful shortcuts in solving the problems. Some problem, let us see. They are asking, show that negation P implies Q and P and negation Q are logically equivalent. So we can do this using truth table. You construct truth table for this, construct truth table for this, observe the output of both the tables. If both are same, we say the logical equivalent. But without using tables, using laws, okay, using laws, try to solve it. So how do we do that? See, I know negation, I know that P implies Q. P implies Q is nothing but, just now we have seen P implies Q is nothing but it is minus P or Q. So I wrote that same negation as it is, this negation as it is. Instead of this, I wrote minus P or Q. Now apply De Morgan's law. What is De Morgan's law? Minus P or Q means minus P and minus Q. Let's apply that here. If you see minus of minus P and minus Q. Minus of minus P and minus Q by applying De Morgan's law. So when you solve it, minus of minus P using double negation law, it becomes P and minus Q. That's what we are expecting. We got the output. Okay, this is a very small and simple example problem to understand. So minus P implies Q and P and minus Q are logically equivalent. So this way you have to prove. Let's see one more problem. See, we are given minus P or minus P and Q and this one are logically equivalent. Show that. So we will take this first. We will take this first. So we will try to apply De Morgan's second law. That is minus P. This is equal to, this is same as P or Q negation. This full part is your Q. So this will become minus P and minus Q. Now again apply De Morgan's first law on this part alone. It is nothing but negation of P and Q. So negation of negation P or negation Q. Now if I little simplify it, it becomes like this, double negation, it becomes minus P and P or minus Q. Now apply distributive property. By applying distributive law, negation P and P or Q is nothing but negation P and P or negation P and negation Q. Now what is this minus P and P? It is nothing, empty, because false, because P and minus P is nothing but false, because one is true and other will become false automatically. So the result is false. and false or something will be the same something. Commutative law, if I apply, it becomes P and minus P and minus Q. That's what we have got the output. So this way, by applying different logical laws, we have seen some laws there. By applying those laws, you have to prove. One way is using by solving truth table. Construct truth table for this, and see, observe the final outputs. If both are same, then we say they're logically equal. Without truth table, using laws means you have to apply like this. You have to apply all these laws. You have to show step by step how you are trying to solve it. Very, very important concept. Show that two compound propositions are logically equivalent. Now the last concept what we are going to study is conjunctive normal form and disjunctive normal form. Let's understand what is conjunctive. Conjunctive, we understood that it is AND operator, right? Conjunction of disjunction. CNF means writing a logical formula such that writing a compound proposition such that it contains conjunction of disjunctions. Conjunction means AND. Of disjunctions, it means P or Q and P or R. This is a CNF statement. Let's see example here. See, these are all disjunctive statements. They are combined using conjunction. Starting normal form name is CNF. It means always focus this first word conjunctive means we are using that conjunction to connect two different statements. See, to connect two different statements, this and this, and inside we have all disjunctions or operator. I think this is in digital logic, it is your sum of product and product of sum. POS and SOP you might have studied. It is very much similar to that. Okay, so in CNF we write conjunction of disjunctions, right? Now, what is principal conjunction normal form? We have seen CNF. It says that the connection should be using conjunction. Remaining all the statements should be with disjunction. But what is principal conjunction normal form? See, if you observe in this expression, we are having three variables X, Y, and Z, right? But does every disjunctive term has X, Y, Z? No. Here, every disjunctive term in the brackets here, we have only two variables. Here we have only two variables. It is optional. Whereas in principal conjunctive normal form, when you are having expressions connected with conjunctions, in this bracket there should be those three variables included, either directly like this X or Y negation or negation Z. So all three should exist with positive or negative. I'll show you the example here, right? See, if there are three variables, the length of the disjunction should be 3, X or Y or Z, and X or minus Y or Z. Here you see we have all three variables in the disjunctions, and they are connected using conjunction. This is called principal conjunction normal form. Similarly, we have disjunctive normal form. We combine different statements using conjunctions. Okay, so inside there can be conjunction X and Y or X and Z or like this. So the connectivity I am doing using disjunction, and the statement inside are conjunctions. Okay, disjunction of conjunctions. See the example, X and Y or negation X and negation Y or X and negation Y and negation Z, right? So we are having multiple statements. Again, this is DNF. What is PDNF? PDNF says that here you should have three variables in this. Here already we have three variables. This is fine. But here we don't have three variables. Here we don't have three variables. We have to include three variables there. See the example like this: X and Y and Z, X and Y and minus Z. Like this, we have three terms each in every expression. This is PDNF. Okay. So remember PCNF and PDNF. Let's see some problem. Determine the PDNF for the expression. So they are connected using OR, but this is in DNF form because I could see there are three variables X, Y, and Z. It is in DNF. Convert this to PDNF. Okay. So there are multiple ways of doing. One way of doing this is using truth table. How can you do this using truth table? Let's see the example of solving this using truth table. So construct truth table here: X, Y, Z. Then you have X and Y. Then you have negation X and Z. Then you have Y and Z. then final output, that is P or Q or R. Okay, so we have to write here true, 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 false, true, false, true, false, true, true. Then you have false, true, false, 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 true. Like this, you have 8 combinations. Try to find out these values. Try to find out x and y. X and y means true, true, false, 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 false. Like this. Negation x and z. Negation x and z. So this also becomes false. This becomes true, right? False. Like this, you write the expressions for all 3. Then apply OR operator, get the final output. Once you get the final output in the table, see, suppose the output here, the final expression output is like this. So I have 1, 2, 3, 4, 5, 6 combinations I have taken here. This output is true, this is true, next is false, next is true, next is true, remaining all are false. So which all expressions got true as the output? First one, this combination got true. Then third one, that is TFT combination got true. Then fourth one, that is FTT combination got true. Now just write them as expressions like this. So how will write this? All 3 are true means X and Y and Z. Or next TFT, it means X is true and negation Y and Z as it is. Why negation? Because that term is F. Okay. Or then the third term FTT, so it means negation X and Y and Z. That's it. We have converted this expression to a PDNF form. How are we doing it? Construct truth table. For this expression, find out the final table value. So you have true, true, false, false, true, false, something like that. When you have expression like this, true, true, false, false, true, false, false, for which all we got true, those combinations you take, input combinations, and represent them as the expressions. Similarly, construct PCNF for this, CXZ, YX. So you have 3 variables, but only 2 are used here. You can convert this into PCNF form. See, without using truth table means you have to apply loss. Obtain PDNF and PCNF without using truth table. How to do this? Let's see. P and Q or negation P and R without using truth table. How to do this? See, we know what are the 3 variables P, Q, R. Which one is missing here? R is missing. So I'll write here P and Q, and I'll write here in brackets I'll write R. Okay, P and Q are R and minus R. Okay, let me just erase this. R and minus R. Okay, why? With this expression or this can be true or false. It is be same, this only, right? So this is yielding true or false. Okay, so now when I expand this, this becomes P and Q and R or P and Q and minus R. So these 2 statements converted to like this using OR operator. Okay, this one statement we have included R, then we have expanded using distributive law, reverse distributive law we have applied, and we got the expression like this. If you see, now we have PQR in the expressions. Similarly, you can do for negation P, this part as well. This part, negation P and R. So here Q is missing. I'll write here or this in bracket or Q and negation Q. Like this. Next, expand this using reverse distributive law. It is nothing but minus P and R and Q or minus P and R and minus Q. That way you got all the terms here. So this way, without using truth table, you can convert them into PDNF and PCNF. Okay. So some practice problems from this unit. Determine PDNF for this expression using or without using truth table. See, determine PCNF and PDNF for this expression using both truth table and without using truth table. Another kind of question. Construct truth table for this expression, construct truth table for this expression, apply De Morgan's law to find the negation of these statements, or determine whether this expression is a tautology or not. Okay, so these are some simple exercise questions which we can expect in the exam. So please practice these problems, try to solve them, and if you have any queries, you can post under the video your query. I will try to answer them. Okay, please practice them. So with this we complete our unit 2 of the course Mathematical Foundations of Machine Learning. So next we will, in the next lecture, we will move to unit 3 about no abstract algebra, algebraic structures, right? Thank you.